Okay, so I'm going to quickly explain how we can do this new set of homework number 6. So the first question is, we have a tapered cylinder that is fixed to a wall. So here is the wall, and this support is fixed to the wall. And the cross-sectional area is, we have different cross-sectional areas. So is A1 here, and this side is A2. So the area at the bottom is A1, at the top is A2. And the length of this bar is L. Now it says find the deflection at point at the end of this bar. So if you have a point here and you apply force P, then we want to see how much this deflects. So if you graphically want to make the deformation, some visualization of deformation. So it is going to shrink down a little bit and going to extend like that. So this is going to shrink down and going to extend because the mass is same, conservation of mass. So it has to shrink, right? Continuity equation. And then this is delta, the deformation of that point because of force P. So we want to find a relation for that using energy methods. So again, as we know, the most obvious choice in energy methods is to start with the energy of a part of system. So in this case, if you consider a cylindrical cut, so consider a slice or cut like that at distance with respect to bottom x. So let's say we have an x coordinate starting at the bottom. So here x0, here xl. And then we consider just one infinitesimal tiny slice. So if that's x, the length of this bar is dx, infinitesimal. And because this is infinitesimal, we can approximate this curvature. We can say this is just constant. See that? This is just constant. So we can approximate that curvature with just a constant value, exactly like Riemann series we did in integration. So in fact, this one, we have a bar like this, right? Which the length of the bar, can use this formula. The length is L is dx. And the cross-sectional area in both sides is A as a function of x, because area changes, right? It's not going to be the same. So it's A of x. Now if you consider this entire taper beam as an infinite number of this constant area sectional bar connected together, then we can do something. We can use this formula. So for this small bar, I'll write the energy, internal energy. So internal energy of this small bar, because it's infinitesimal, du is not u, it's a small energy, is equal to, then I use this formula. So what's the force in this bar? Well, if this P is same everywhere across this bar, so the force in infinitesimal bar is P. So P remains P squared. L is the length of this bar, which is dx divided by 2 the area of this, which is ax, time module of elasticity. So this is the small infinitesimal energy of this cylindrical slice at location x. Now my total internal energy, UI total, is just summation of all infinitesimal energies from here to here, all the little parts, all the little slices, right? So if this is infinitesimal, that summation becomes integral of p squared dx over 2 ax e from 0 to the total length of this tapered loop. Right? Now, here p is a constant across all the x. P is not a function of x. E is not a function of x. 2 is not a function of x. Just take it out. So you have p2 over 2e integral 0 to L dx over ax. So you have to find, now I don't solve the rest of it. You have to find a relation for cross-section of area, not diameter, not radius, the cross-sectional area at this point. You have to find the relation for this versus x. This relation is very simple. It depends on A1, A2. And then you have to integrate it. So at the end, you get UI total, the internal energy total, become a function. Now you have to find this functionality. It becomes a function of P, modulo of elasticity, area 1, area base A2, and the length. Alright, you don't get x. X is just a variable of integration. All you get at the end is this. And then, if you take the derivative with respect to P, give you displacement at this, which is simply the derivative of this with respect to P. Now you should do this. If you note, we can solve this. Now you can pause the video and practice and solve it and finish it. And after you do that, then you can consider another approach for the same problem. So let's just consider another approach. This is the energy approach. Now, let's just consider another approach to solve to get exactly the same result. So now let's say we divide this into small slices. So one we have here, one here, and then infinite number of slices. One here, right? So in fact, you end up with a series. If you look at it from the side view, you end up with a series of bars connected together. And this line is going to approximate the tapered shape of the bar, the total bar, right? Now, if you consider each one of these guys is a spring, right? Because it's a bar, and it acts like a spring. So if this is 1, this is 2, 3, dot, 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 and this is the spring number n, then you have K1, this is spring 1, connected to a spring K2, connected to a spring K3, connected to the spring Kn. When n goes to infinity. So in this approach, you have n number of spring which is infinite. Number of spring which is connected, they are all connected in series. This is series connection. And you have a force P. So we studied before from the method of equivalent spring that 1 over K total is 1 over K1 plus 1 over K2 plus dot 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 plus 1 over Kn. So if you find the spring constant of each one of these and sum them up, then you get the total the spring constant of this tapered beam. Well, if you have the spring constant of tapered beam, you can find deflection here. What is deflection? Deflection P is equal to total spring constant times delta. So delta is 1K total times P. So if it happens that you have this from here, then you can immediately find delta. And it should be exactly equal to the energy method. So this is another approach. I would recommend try this and find the formula. Now let's say you find the formula. Then when you find the formula, you can use it in problem number 4. Right, or problem number 5, the last problem. The last problem, we have a beam, a composite beam like that, and then you have some loading on it. For example, let's say you have 10K here, and let's say this is fixed. Right? Now if I want to find deflection here, I can say this is one spring, series connected to a spring 2. So you have a formula for this coming from the energy method, K1. The spring constant of tapered beam comes from energy method. You get it in problem number 1. For K2, it's just a bar. This is the formula. So you can find equivalent spring. Very quickly you can find the formation. You don't need to do all the integration from scratch. Also, if you have a torsion, because you have an arm and you have a loading on that rigid body, so you're going to have a torsion, right, a twisting effect. Then the torsion of the spring constant of this constant sectional bar is right here. And the one you get from question number 2, the torsion of the spring constant of tapered one. Then you can immediately find the effect of torsion. In fact, you can solve the last problem. So this is just a brief overview of what you need to know before you attack this homework problem. And yeah, I just wanted to share it with you guys because you have questions. Some of you guys had questions about how to do this. So hopefully that's going to help you. Thank you.